Good afternoon. I'm going to talk to you this afternoon about timber frame construction. We'll look at it through a series of eyes from the point of view of procurement, construction on site, subsequent surveying and alteration to timber frame properties. I have spent some 15 years or so in the timber frame or working for the timber frame industry, doing structural engineering design. And it's a vast subject, but I want to try and give you some insights on things that commonly can go wrong, particularly with the procurement. So this afternoon, we'll look at issues to do with buying timber frame. We'll look at the design stage of it. We'll look at construction, and then finally, as I said, inspection and alteration. But let's start off with some definitions. What actually is timber frame, and where is it in the market at the moment? Well, we have to start off with a rather low point for timber frame in the early 1980s. It had become popular. It had 40% of the market, and it was growing. And then a documentary series on Channel 4 called World in Action decided to put rather a spoke in the wheel and managed to get onto a site with a hidden camera and filmed several defects in the timber frame. Those defects were real, they were there, they weren't made up. The only thing one can say is that from a balance point of view, and having worked for the NHBC at that time, all house building was bad, even traditional construction. But the programme managed to give people a fright on timber frame, and its market share plummeted to less than 10% within a year. It's been a long haul back for the timber frame industry. In the last year to June, the completions for homes, 170,000. That's up 8% on the previous year. That's showing reasonable growth, perhaps helped a bit by the government's Help to Buy scheme. Timber frame has around 28% of market share of that house building market, and it's rising. So house building completions rising, share rising as well. It's a busy time for the timber frame industry, and it's having to suck in more and more people into its ways and means. It has very specific techniques, as you can imagine. Interesting, this next statistic, around 50% of self-build projects are built with timber frame. And I think the reason for that is that if you go into your local Barrett's or Bovis site and sign up for one of their plots, you're buying a package. You're buying a complex mixture of trades, services, etc. And you're having a package to give you a ready home that you move into. If you're building your own house, it's a complicated package to try and procure on your own, and many timber frame companies have actually streamlined that package so that much of it can be obtained with a single signature on a single contract. And that's made timber frame very popular with the self-build market. Residential buildings, 65 to 75% of the market. What comprises the other 35 to 25%? Well, it's mainly similar format buildings. Motels and hotels are one good example of timber frame. If you stay in a Premier Inn or you stay in a travel lodge, that's almost certainly a timber frame building that you're staying in. And these are volumetric buildings. They probably build the room to quite a high degree of completion in a factory and then take it on a lorry and place it on site. Student accommodation, that's also a popular choice for timber frame construction. Now, there's a lot of talk of off-site construction. That's the new buzzword. It's meant to be a way to improve quality in construction. And of the off-site construction, timber frame has around 70% of the market, and by turnover, it's about 3 times these other 4 methods put together. So it is definitely the market leading form of off-site construction. We'll look at structurally insulated panels and cross-laminated timber in a minute. Precast concrete panels speaks for themselves, and there is a steel equivalent of timber frame using light gauge steel to form close centre studs. That's also becoming popular in construction. And most properties, even timber frame properties to a limited extent, will have non-load bearing partitions formed with lightweight steel frames. Just to get some terminology that you may come across with timber frame in context. Where the timber frame panels are the full height of the building, that's referred to as balloon construction. It's not very common in the UK, but you may see it on a property where you have perhaps a big gallery running full length of the property, so you have the walls of necessity have to go full height. Very difficult to find timber that's straight and would go that height without having unsatisfactory bends in it or cranks in its line. And these sort of galleries are very popular with self-builders now, and let's face it, you won't get on grand designs unless you've got a feature like that in your house building project. What's more common is what's referred to as platform construction. The walls are single story, they're erected, then the floor goes on, and then the next story is built on, and then the roof or the next floor again. So you're doing 1 story at a time. So the panels are only single story height, quite manageable, quite easily formed in solid timber. When timber frame companies are doing the erection themselves, they typically make a panel to slot into the stair opening during construction as a safety feature, sometimes referred to as a crash deck, although it always has a sign attached to it saying it's not designed to take any load. But by far the most common form of construction now. Right, cross-laminated timber, and you'll see from the left-hand image, this is a bit like plywood, only it's more substantial thicknesses of timber, 45 millimetres, laid in boards, and then alternative layers are reversed at 90 degrees, glued together, and it produces a very, very strong panel which can be used for walls, floors, roofs. And this image on the right-hand side, which I confess I pinched off the internet, I don't know where it is, but it looks very tidy, suspiciously tidy site to me. And you'll see that all these are solid panels. I think the roof are CLT panels. These are probably glulam beams, but everything else I think is cross-laminated timber. I think this material's got a lot of potential, and I can see it growing in the coming years now in its use. Got all the advantages of timber in that you can work it easily on site, cut service holes on site if you need to, but at the same time it's lighter than concrete, but very strong, very, very strong. Structurally insulated panels. SIPs, as they're usually known, consist of insulation with a layer of OSB glued to each side. And on the right-hand side now, you can see a building actually formed with SIP panels. But notice that they're like the old ice cream with wafers. They're sort of, the insulation's cut back a bit so that you've got an overlap of the OSB over the insulation. And the reason for that is that where panels are joined, or where you have concentrated point loads coming down, you insert a timber stud on site into that gap between the panels, and then you glue it all together. This means that you've got very few timber cold bridges across the panel. It's nearly all insulation, apart from where you've got point loads and the occasional panel join. Somebody at the last lecture asked me about vapour barriers. There's a vapour barrier on the inside, but obviously this is a mock-up for demonstration purposes. We incorporate studs, as I said, where there is concentrated point loads. It also strengthens the panels and allows them to span further if need be. But simple joints in the panels can be formed with splines. And the panels can be routed out, and 15 thick orientated strand board, OSB, can be glued into those gaps to give you continuous insulation across the board joint. By far the most common application of timber frame is what we refer to as open panel construction. So the timber frame comes to site as a timber carcass. That's ends, bottom rail, top rail, studs at 600 centres, and then the insulation, plasterboard and the vapour barrier are fixed on site. The breather membrane on the outside is factory fitted. And the idea is that the vapour barrier is 3 times more impermeable than the breather membrane, which means that moisture that's in the wall can leave it easily, but moisture doesn't enter the wall very easily because of the, because of this vapour barrier on the inside. A few things to bear in mind. It's quite common for there to be a head binder. This is an industry standard practice. That's nailed on site, and the idea of it is it binds all the panels together during construction so that it helps keep it stable. But another important application is that the joists and the studs, if they do not align, then you need to have that double layer of plate to help distribute the loads onto the studs. If you arrange for them to all line up, then you don't need the double layer of plate, but you can imagine the difficulties and the coordination involved in making sure they all line up.
So on the vapour barrier there, that detail shows it interrupted by the joists.
Yes.
Is that an acceptable practice, or should that be wrapped around the joist ends and up?
It's not normally wrapped around the stud, so I think the answer is an acceptable practice.
Okay.
Where there is a floor junction, there's normally just a header joist, and then the panel above will sit partially on the joist, partially on the head panel. That shows a masonry cladding, obviously typically brickwork. A 50mm cavity tends to be the standard. 140 joists, so the whole wall is 300, which is basically the same thickness as you would have for a brick and block construction now, where you'd have a 100mm cavity. You may ask, 38 by 140, that's a rather odd size for the joists. It's, of course, a hangover from Imperial. It's 1.5 inches by 5.5 inches, which in itself is a bit of an odd size, isn't it? It's an North American size, although it's now sourced from Scandinavia. They produce timber to North American sizes. You do get occasional projects where a more traditional 2x6 timber is used, but 38 by 140 tends to be the standard for external walls, and 38 by 89 for internal walls. Now, I mentioned the masonry cladding. We tend to be sort of a bit married to our masonry cladding in this country. We like brickwork. It's the most popular finishing material for buildings to clad them in brickwork or blockwork that's rendered. But there's no reason at all why you can't put battens on the timber frame and then either have timber boarding with render on it, tar hanging, all kinds of finishes can then be applied. And I think this is one of the strengths of timber frame, is you then have a wall, an external wall that's perhaps only 200 millimeters thick or even narrower. Is ideal for small extensions to properties where you're tight on space. It gives the client much more usable space in their building, and it makes the construction simpler, quicker and cheaper. It's worth adding that you can mimic that construction with masonry. You can have masonry on the inner skin, battens, a ventilated space, and then your outer finishing material. I've only ever known it to be done on one project, but there's no reason why that shouldn't be done. It would comply with the building regulations. Now, just to show that nothing's really new, this is a timber frame property dating back a couple of 100 years with tar hanging on it. Managed to get planning permission for alterations to that quite easily, despite a listing status. Now, timber has certain obstacles in people's minds. It burns easily, it rots, it's not very strong, not very robust compared with steel or concrete. So let's examine those common misconceptions about timber and see what we can actually do with it. Timber will resist burning or ignition up to 400 degrees centigrade, provided it has a plasterboard lining. I must make that clear, it must have a plasterboard lining. But it will resist quite a high temperature. It chars at a uniform rate, so you don't get a sudden weakness in the material at weak points, etc. The charring tends to be fairly even along the whole length of the timber. Timber has low heat conductivity, and so fire will not be transmitted from one zone to another by the conduction of heat along the structure, which can happen with steel, for instance, which readily conducts heat. Timber does not deform at high temperatures. Again, steel will yield at relatively low temperatures. And timber chars around the outside, around the outer surfaces, which then protects the inner part of the timber from decay in the fire. And there are published standards, the British standards, now Euro codes, which actually gives you a calculation method for determining fire resistance. And obviously large section members will last a long time in fire.
Is the sap content of different timbers or the way it's dried out, like kiln grind, etc., does that have any effect on the fire-bearing quality of the timber?
Not to my knowledge. In doing any calculations, etc., there's not normally any prerequisite of what species of timber it is. But having said that, nearly all constructional timber in this country is Scandinavian whitewood and redwood. So whether a hardwood may have a different fire characteristic may be the case. I have to say I'm not certain on that. Rot and infestation. Timber will not rot at moisture contents below 20%. So as long as we can maintain a content lower than that, timber will not rot. So that's why it's important that roof spaces, underfloor spaces are well ventilated to prevent rot taking place. Normal construction, good building practice will make sure the content doesn't get above 20%. Timber which is in contact with masonry, such as the sole plate, wall battens, tiling battens, These are always treated, and it's generally a warranty provider requirement that they're treated. And of course, there's certain parts of the country where there is a requirement for construction or timber to be treated because of particular infestations that are prevalent in those areas. We look at the strength of timber versus masonry, and we need to consider two facets. We need to consider the axial load, that's the load that transmits vertically down through the studs as part of the weight of the building above. And we need to consider the load on the side of the wall from the wind. Looking at vertical loads, we take a 100mm block wall, 3.6 Newton blocks. That will carry around 50 kilonewtons a metre. That's about 5 tonnes. That's quite a lot. A timber frame wall with 38 by 140 studs, provided it has plasterboard or sheathing. I can't emphasise that strongly enough. Its strength is nowhere near the same without some form of lining. That has a load of 27 kilonewtons a metre, a load capacity. That obviously is almost half of the masonry capacity, but bear in mind the fact that a timber frame wall is carrying a lot less weight. It doesn't need to do such the same job as masonry because the walls above it are light, the floors are light. If we then introduce openings into the wall, and I've chosen 440 piers, 560 wide openings, you can see that the masonry capacity goes right down to 17. You can increase that by using higher strength blocks, but the only problem is once you go above 7.3 Newton blocks, you're starting to compromise the thermal performance of the wall. Timber frame, on the other hand, stays the same, 27, because you just put extra studs in either side of the openings, and you can do that as much as necessary to carry the loads that are required. And I'll bring to your attention that the load-bearing capacity of the timber frame is generally limited by the stress on the side face of the sole plates, where the studs bear onto the sole plate. Timber is very weak on the side grain. You can press your thumb into it if you try hard enough. Along the grain, timber is very strong. So sometimes when we have high point loads in timber frame, we actually specify that the studs under the load bear directly onto the concrete underneath or onto the masonry underneath. And when it's on a sole plate, we limit the capacity of the stud according to what the sole plate will carry. You could increase that by using higher strength timber for the sole plates, but 38 by 140, as far as I'm aware, only comes in C16. I've never seen it in a higher grade than that. Now, flexural strength. Those structural engineers amongst you will know that a traditional construction like 100 brick and 100 block, even at a story height, can be difficult to justify by calculation. And I always constantly try to persuade architects and architectural designers to keep within the limitations of approved document A when you can, because once you come outside of it, it can get tricky to justify masonry. On the other hand, the timber frame, 38 by 140 studs, that will carry plenty of wind load, as much as you're likely to experience. If you need to improve the wind load resistance of a timber frame wall, you just close the studs up. It's very difficult to improve the characteristics of the masonry because the flexural strength of masonry is constant across all the grades. And even if you make the wall thicker, for some reason or other, the code requires that you reduce the stresses it can take. So your improvement in performance is offset by having to use lower stresses. Now, Now, let's look at some of the advantages of timber frame. It's got good eco-credentials. It's sustainably sourced, it grows on trees, and the trees are constantly replanted. They say that for every one that's cut down, they plant 3. One to replace it, one for the remedials you're going to subsequently need. I always joke, but it's not true. It's not true. And one for the future. Timber frame buildings generally have very low carbon footprints because they have good insulation properties. They're generally fairly airtight as well, so you don't lose much heat from them. Perhaps procurement is where timber frame has some of its biggest advantages. From a contractor's point of view, he can write one order and have a building brought right up to the roof. It's a form of de-skilling, having it factory made. Timber can be easily worked on site by carpenters. Now, in a perfect world, timber frame comes to site and it doesn't need to be worked on site. It all fits perfectly. All the service holes have been thought of beforehand and are in the right place. In practice, a little bit of fettling is often required. But that's not too much of a problem, providing it's done in the right places and it's sensible. You can form and shape timber frame on site. Timber frame isn't weather dependent in the same way that, say, masonry is, because you cannot use mortar on a falling thermometer below certain temperatures. You can't use mortar when it's freezing or close to freezing. These constraints don't apply to timber frame. You can, as long as you can bang nails into timber, you can carry on constructing timber frame. So it has that advantage of greater certainty during cold weather periods. It's just worth emphasising that work's done in a factory. The people who do the work, because there's a process involved, the amount of training and experience they need is much less than a carpenter would need on site to fashion a timber frame building on site. All work is sort of carried out at waist level on benches. You have saws which are set up and you generally have computerized output which tells the sawyer exactly what he needs to cut, and all the nailing together is done with machines on benches so that the assembly can be done very quickly. Another advantage of timber frame or timber frame floors is that a trend is now prevalent in the industry where floors are made up in cassettes. See, there's a cassette with a stair opening in it. They're made up in the factory, taken to site whole, and then they can be craned in position and a whole floor laid easily in one day, giving a shortened program on site. Now, I remember once taking a car back to the dealership because it had an unsatisfactory aspect to its performance, and the salesman telling me it was a feature of the car. It wasn't a design defect, it was a feature. So let's look at the features of timber frame. There's a lead-in period. You can't go into your timber frame manufacturer on a Friday with a list of what you want and have it delivered on the Monday. There is a few week lead-in period. Supporting high-level masonry, I'll illustrate this point in a minute. There's a lack of load spread with timber frame buildings. Again, I'll illustrate that. And then there's our old friends, shrinkage and settlement. Settlement within the timber frame. These are aspects of timber frame that need to be carefully taken account of. There is a lead-in program because, in theory, every stick of timber in a timber frame needs to be analysed, or at least divided up into groups and analysed. Unlike masonry, where you have approved document A, and if you follow the protocols in there, you don't need a structural engineer. You can specify a building without a structural engineer. Timber frame needs a structural engineer. He needs to look at all the studs, the racking, distribution of loads, etc. You need extensive drawings to allow fabrication to take place. Again, every stick in the building needs to be scheduled because that's all fed onto the shop floor and a bundle is made up and then it's all nailed together. So you need a lot of drawings, you need a lot of calculations. That means the design and the engineering can be costly. But if you've got an inner city site, say in London, you've got very limited space for storing materials. You can't put skips on the road outside. Timber frame can save a lot of money in preliminaries because your time on site is much reduced and the general process of material being stocked and subsequently used is streamlined. Right, I mentioned supporting masonry at high level. And this left-hand arrangement, where you have a single story going into a two-story building, and this could easily be, for instance, an extension or a projection at the back of a building. If you've got a high-level gable there, if that's in masonry, you can't support it on timber frame, because timber frame shrinks, brittle, masonry is very brittle, and it won't like movement in the supporting structure. So what can you do about that? Well, we always try to persuade people to form the gables with tar hanging, brick slips, boarding, render, one of a number of possibilities. And then you can form the whole party wall structure in timber frame. If you must use masonry, the only two options are to use masonry right down to the foundation. Now that's not out of the question, but in an industry where sequence of trades is very dominant in dictating the process, that has got a lot of disadvantages. You need to bring masons on site, have scaffold put up for them to bring that masonry wall up, and then the timber frame people need to come in subsequently and work around that masonry wall, which has the potential to be unstable until the timber frame is in place. You can leave the timber frame down around the wall so the masons come in subsequently, but then you've got a small amount of timber frame that somebody's got to complete after the masons are finished. And also the timber frame walls may not be fully stable until you've completed all the floors and all the roofs. So that isn't normally a very satisfactory way. Sometimes if builders are erecting the timber frame themselves, they will work around it and take it on board. So when I get a project land on my desk, the first thing I always do is go through all the elevations, looking for any circumstances where there is high-level masonry potentially sitting over a timber frame. You could, of course, put a steel frame up to the underside of the masonry. If you've got no walls underneath it at all, then the mason's going to have to lay his bricks or blocks on top of a sloping rafter, which is not easy. Now, I mentioned load spread. If you apply a load at high level, with a masonry structure, you'll get that load to spread. And by the time you get down to the foundations, that load could almost spread over the length of the building. Timber frame, you put a cluster of studs under that load and it arrives at sole plate level as a point load. Well, that's the way the industry works, it's the way I work. It's always taken to be a point load. And so you've only got the spread of that load over the substructure, which is limited, 2 meters, 2.5 meters perhaps. So the foundation designer needs to take into account that he's got concentrations of load. In extreme cases, he may need to put pad foundations in underneath them and then hope the architect doesn't change the layout subsequently and I move that point load somewhere else. Now, timber shrinks. You can see that nice air gap. Masonry doesn't shrink, or doesn't shrink to the same extent. So what does that mean? Windows are normally fixed to the timber frame on brackets, and so if the aperture in the masonry exactly matches the window and then the timber frame shrinks, that window is going to foul the masonry underneath it and either buckle the masonry, buckle the window, damage the brackets, do one of it. So it's necessary to leave gaps between the sills and the masonry to make sure that there's no contact between them causing damage. And that the amount of that gap varies as you go up the building. You also need to leave a gap at the eaves so that the timber roof structure doesn't settle onto the masonry skin that's outside, and the same at the verge. You also need to leave a gap underneath the verge and the brickwork. I'll come back to this a bit later, but this, you don't see this published anywhere, but I've had a few experiences of this where they hang bifold doors from the timber frame, and then, surprise, surprise, sort of a month later they jam in and won't close properly. So the door manufacturer comes back, planes a bit off, and then a month later they jam in again because that shrinkage process does take a few weeks to occur. As the thermal element of building regs become more onerous through the 80s and the 90s and the 2000s, insulation above the ground slabs become thicker and thicker. Now, the timber frame industry initially started increasing the number of sole plates. The shrinkage that causes the problem doesn't occur in the studs. Studs hardly shrink at all along their length. All the shrinkage is in the rails and the sole plates. And so when you have deep first floor joists and when you have lots of sole plates, you get lots of shrinkage. Now, this has been partially remedied now because standard practice is to put a layer of blocks underneath the stud wall so that the timber frame actually sits on blocks above the level of the floor finishes. And therefore you only have the limited shrinkage that occurs in the bottom rail and in the sole plate. First floors are commonly formed from engineered timber now, which can either be metal web joists or timber I-beams. They have very little shrinkage in them. The rim board around the edge of the first floor, that would also be engineered timber, very little shrinkage. So the shrinkage problem is getting less and less. It's less of a problem now. Settlement is something that's often not mentioned, but with the best will in the world, when a carpenter nails timber components together, he's not always going to give the timber the nails those extra 2 or 3 knocks they need to absolutely close up gaps between timber components. And sometimes it may not be easy to do. The timber isn't perfectly planed, perfectly matching each other. You will get slight gaps. As the building's loaded, those gaps close up, and it contributes to what we see as shrinkage, although strictly it's settlement. Whilst it's consistent throughout a building, it's not really a problem. But if you have a building with very concentrated loads in certain places, those gaps can close up more quickly and more completely than the rest of the building will close up. It's a particular problem with heavy loads and a particular problem where the workmanship on the timber frame is poor. I come across this particularly on one building where there was a significant slope to the floor. We didn't initially know what the problem was, but we noticed that all the slopes pointed towards areas where there was concentrated loads. There was a suspicion that perhaps there hadn't been proper allowance for the loads in the design of the timber frame, but there had been. And when some further investigation took place with some opening up, that seemed to be the problem, that there was settlement in the timber frame. Now, timber frame design. Worth just being aware of what terminology is used. Timber frame is seen as a design and detailing process, and the man in charge of it would generally be a designer, and he will be an experienced timber frame technician. And the structural engineer is often employed by the timber frame designer, which is the opposite way around to most buildings, where the structural engineer will lead the design and the technicians will work through the structural engineer. That's because historically there were standard details used, standard protocols, and the engineer's involvement was perhaps very limited. Now, it's getting near Christmas, so I'm allowed to put my wish list. What I'd like for Christmas, please. Time in. Timber frame engineer is normally employed by the timber frame supplier. The timber frame supplier will not employ the engineer until he has an order. Responsibilities, this is another aspect of timber frame. Most people think that once you've got a superstructure that's in timber frame, nobody needs to do anything anymore. The architect packs up and goes on holiday. The structural engineer employed by the client goes on to the next job. And certification is also something you need to be wary of. So just going back to that timing, the foundation designer cannot design the foundations without the timber frame loads. Timber frame loads will only come about once the timber frame designer, the timber frame engineer has been employed. So to avoid a lag in the design program and in the construction program, the timber frame supplier needs to be on board fairly early. With a complicated building, I find it impossible to give any foundation loads for the foundation designer without carrying out perhaps at least 75% of the design, because if you've got transfer structures, you can't easily calculate how much load is coming down the outside of the building until you've designed the transfer structure. Timber frame supplier will appoint that engineer, as I said, and then pass those loads on. Responsibilities. I mentioned the fact that a lot of people just sort of move on to the next job once there's a timber frame supplier on board. Obviously the foundation design has to be done by the client's engineer. It's not the responsibility of the timber frame company. The support of masonry over openings and projections. That is, again, not the timber frame supplier's responsibility. Now for openings up to, say, 2.5 meters, standard lintels are going to suffice. If you've got a wider opening, it may require some clever engineering to support the masonry with a member that is supported on the masonry either side. Movement joints. A building of any size, any length, is going to need movement joints in the masonry, not the timber frame supplier's responsibility. That needs to be the building designer, the architect or the engineer employed by the client to specify those joints. This is a common argument. Balconies and porches. Balconies and porches are normally fixed to the masonry, and so the timber frame manufacturer will not normally engineer them on the basis they'll be built at a different time to the timber frame. It does somewhat fly in the face of the contractor's dream of having everything taken care of by somebody else. So it's very common for the timber frame supplier to be asked to support the balcony or to support a porch off the timber frame. And they will do so, but it can't be assumed that they will do it unless they're asked to do it. Non-fabric issues. Things like means of escape distances, headroom over stairs. These are all the building designer's responsibility. A timber frame designer will normally check that there's sufficient headrooms. If there isn't sufficient headroom, he will flag it up, but it's not his problem to get round, it's the building designer's problem. Certification. Warranty providers, and I've named two, the NHBC, Premier Guarantee, there are others. In the past, they have always required certificates, and a certificate needs to be provided by an independent person to say the timber frame design is proper, compliant with the codes of practice, compliant with the warranty providers' specifications and requirements. The reason for that is because timber frame was always seen as being specialist, and the NHBC didn't want their inspectors to have to assess whether or not it was okay. And it's a certificate of design. It's a certificate to say the design and the drawings are okay, not the site construction. It's that the drawings and the design are okay. And that certificate should be on site as and when, if not before, the timber frame comes to site.
So who would normally be that person who provides that?
Right, the NHBC has a list of registered certifiers. They do not necessarily work for the timber frame company, and they must be independent of the design process. So in a small timber frame company, the designer can't certify his own work. It needs to be perhaps an outside person. But what I emphasise here is that it's the responsibility of the builder. It's a warranty provider requirement, it's a requirement on the builder, and a builder is responsible for organising that certification. He can go to anybody who's a registered certifier. He can ask the fabricator to provide it, and I'm sure they will. There is a common perception that all the certifier does is fill out an A4 size form and sign it. In fact, he's signing that form to say he's checked all the drawings and checked all the calculations. So it's obviously quite an expensive document. And therefore, human nature, being human nature, builders and contractors try to avoid having to provide one until the last minute. And nearly all certificates that I get asked to produce are after it's built. And they'll say, well, what are you going to do if I'm not happy with something and it's already built? What are you going to do? You'd have to take the building down and sort it out. People start to look a bit worried then. The NHBC did a random sample, I think, of 500 sites and found that no more than half of them had a certificate on site when it should have had one. These days, there are schemes where if the designer and the fabricator belong to a quality assurance scheme, the standard certificate isn't required, but then you would still need evidence that that scheme is in place, the quality scheme is in place. So if you're responsible for procuring a timber frame building, make sure somebody's appointed to supply the certificate at the time that the timber frame comes to site. Right, site construction issues. I'm going to look at accuracy of the substructure, scaffolding, provision of shrinkage, accommodating services. That old chestnut applies, of course, to all types of construction, not just timber frame. This is the stage of construction where timber frame would normally arrive. The substructure's been built, the slab has been laid. And of course, the timber frame is made in the factory, over there, to the drawings. The substructure is made in the ground, in the rain, in the howling wind, in the mud, to what people think the drawings said. And there is a very limited scope for disagreement between the timber frame and for the substructure. It's actually surprisingly more common to have level variation in the substructure than it is in the actual line of the substructure, but both problems occur. Warranty providers do stipulate maximum tolerances and deviations that you can have. And if you're outside of those, the timber frame engineer would normally have to come to site or to have all the deviations given to him, and to assess whether the timber frame can be locally strengthened, whether the substructure needs to be altered, albeit perhaps with the timber frame taken down. A messy problem, so it's worth being doubly sure that the substructure layout is accurate. Now, scaffolding. Timber frame goes very fast, and you'll interrupt that process if you have to wait for the scaffolders to come back to site to raise the scaffolding. So you'll often see quite tall scaffolding on a building site with nothing up at all. And that's because it's likely to be a timber frame building where they put at least the poles up to quite some height so that the timber frame erectors have got continuity. They can keep working. They don't have to stop and wait for the scaffolders to come back to site. You'll notice here that the poles have been set back from the timber frame walls, and also some of the cantilever poles are also in a position so that they can be pulled back. And that is, if you want to use the same scaffold for the timber frame and for the outer masonry, then you need to have provision to create a gap between the scaffold and the timber frame for when the brickwork comes up. So timber frame comes right across, and then to fix your masonry, you pull the scaffold back. There are set diagrams and details for scaffolding. It has to be robust so that it can stand up on its own without being fixed to a building. And you'll notice that the Trade Association do say that scaffolding for timber frame buildings needs to be designed on a job-by-job basis. Right, we discussed shrinkage earlier. I mentioned these tolerances. A particular issue here with ground floor windows, ground floor door openings. And if we look at this house here, what I bring your attention to is this joint around here. If we continue boarding across the first floor to subsequently receive shrinkage, receive render, as the timber frame shrinks, that board risks buckling and disturbing the render. So it's normal practice to allow a gap at each story for the render to close up when the timber frame shrinks. Now on this particular project, there was a problem with these doors here jamming. And after they'd been to site 3 times, the door manufacturer measured the distance from the wall from the floor to the lintel over the opening. I said, hey, there's a deflection problem here, because they noticed it was a bit more in the middle to what it was on the outside. And they went away content with the thought it was somebody else's problem, and it was put back on my desk. Now this beam carries very little load. It's just carrying a small amount of roof load on it, and the deflections are actually quite small. And bearing in mind this would be designed to carry snow, and it's got no snow on it at the moment. The deflection isn't actually an issue at all. It's shrinkage and settlement on the timber frame that was causing the doors to jam. So I do try to warn people now that if they're having ground floor doors, the door manufacturer needs to allow plenty of gap above the door for shrinkage and settlement in the timber frame. Services. Timber can be notched and timber can be drilled, but only in areas where there's low stress, and the sizes of those notches and the size of those holes are limited. There is published information, certainly it's in the NHBC handbook, and there's other trade information. Timber frame manufacturers normally produce a handbook which also has the zones which tell you where you can drill holes, where you can notch joists. All those things are spelt out. Everybody knows it apart from plumbers and electricians, unfortunately. It's unfortunately too common a problem that I get asked to say whether something's still safe or no, having been notched or drilled where it's not meant to be notched or drilled. It seems to me perhaps a training problem, a supervision problem, definitely not a communication problem because the information exists. Now, what the industry has come out with is metal web joists. So you've got loads of room there to move all your services, or your cabling, or your ducting within the floors. You must not, never ever, notch these members or drill holes in them, because they're doing all the work. That gap there is for all your services. A couple of things I'll point out with this image. See special hangers for carrying these metal web floor joists, which can be as deep as 1'6". They can be quite deep. You need special hangers that give them support to quite high up to stop them twisting at the support. All the main manufacturers produce them: Cullen, Simpson Strong Tie. Notice steel beam in a timber frame building is a common requirement that all floor beams are the same depth as the floor, and if there's any sort of span involved, unfortunately you have to use steel to limit the depth. So common process, you have a timber plate fixed into the web and then you have your hangers nailed to it.
Why didn't they use a wall?
Sorry?
Why didn't they use a wall?
Ask the building designer. It could be their wall was built afterwards. Not certain. Yeah. It can often be a sequence issue. People want a timber frame to go up first and then they come along and do the internal walls afterwards. Fair point, though. Fair point.
Because I didn't think about it then.
Yeah. There's probably not a good reason. One thing to bear in mind with metal web joists is that they're factory made. You cannot alter them on site. They have to come to site fabricated to the correct length. That involves a bit of thinking, a bit of ordering. Obviously, if they're part of a timber frame project, a timber frame manufacturer would do all that. But if you're just using them in a traditional masonry building, then they have to be ordered to the specific length. I-beams and solid joists can be cut on site to suit, can be ordered in stock lengths and cut to suit on site, but not metal web joists. Going back to our sit panels, it's not possible, or certainly not easy or feasible, to incorporate services within a sit panel, and you're also undermining its thermal properties. So it's quite common to produce a zone on the interior of the building where all your services can run. Now, there's a lot of surveyors out there, I'm sure, inspecting timber frame properties. How do you know if a building's timber frame? What sort of non-intrusive investigation can you carry out? What is the nature of spandrels in the roof space might give a clue. The density of substrate above the windows, I'll just illustrate that with an image in a minute. Movement gaps under the sills. This is commonly cited as one way of telling whether or not it's timber frame. But of course, if those gaps that I mentioned you need under the sills do their job, they won't be there anymore. So you can't tell because the gaps won't be there. Information held by the building inspector or warranty providers. Well, I don't know if any of you have ever tried to access that. It can take time, it can be costly, and it doesn't always provide the information you want for some reason or other. Now, a little word of warning. These are floor cassettes. I illustrated them earlier. They're all in place. Now, if you're looking at this building after it's complete and you want to know if it's timber frame, you may be able to tell that the floors are cassette. So you may think, floor cassettes, timber frame. Well, these are made by a timber frame manufacturer, definitely, but it's actually a masonry building. You can see the masonry here on the outside. So timber frame components in themselves don't mean it's a wholly timber frame building. If you look up in the roof space, you may notice that the party wall spandrels and the gable wall spandrels are finished in ply or OSB or chipboard, and that may give you some indication it's a timber frame building. But I'd have to bring to your attention that since the 1980s, it's been common for spandrels to be produced by the roof truss manufacturer for the convenience of the contractor. And so the presence of ply, OSB, chipboard on the spandrels doesn't mean it's a timber frame building, unfortunately. It's merely a possibility. You can knock the wall, of course, and if it's got a hollow resonance, that could mean it's a timber frame property, but it's just as likely with a recently built property, it's just as likely to be dry lined. So how do you know whether it's dry lined or whether it's timber frame? Well, if it's dry lined, if you knock the wall above an opening, dry lined would be hollow still because that gap under the plasterboard continues right the way across. If it's timber frame, where the plasterboard's fixed directly to the studs and to the lintels, it will have a solid resonance. You really need to be careful in that it's quite common practice in the timber frame industry to put the lintels up under the floor and to have timber framing underneath the lintel. So if you do use that process, make sure you knock above the opening and under the floor as well. And if you get that solid resonance, it could mean it's a solid timber directly behind the plasterboard. There are intrusive methods which will give you a more definitive answer. You could drill a small pilot hole through the cladding and use an optical device to see what the nature of the main framing is. You could lift floorboards adjacent to the outer walls and be able to see the nature of the outside walls. Now, you might say, well, this isn't really intrusive, but as somebody who has a biological problem with crawling around smelly roof space on my hands and knees, I accept that this isn't easy, but you could use a mirror or use your hand to feel behind the wall plate, and there should be sheathing, and that sheathing will normally stop at the top of the panel, which would be just down from the wall plate. Sometimes that sheathing is brought up to the top of the wall plate, so either possibility exists. I accept not easy to do. If you've got a low pitch, it's not easy to get close to the eaves.
You might have an insulation on as well.
You might have to locally remove some of the insulation. And if you comply with all working at height requirements, you need crawl boards, face masks, and goodness knows what else. So it's almost an intrusive process. So what sort of defects should you look for? Timber frame has got a lot of quality aspects to it. It's factory made to published specifications. It's erected by people who know what they're doing. Just say that with a slight amount of unease. So you wouldn't expect there to be too many problems. This is something that does happen, unfortunately. Timber frame, you cannot have full cavity insulation in a timber frame property. The timber frame cavity's got to be allowed to breathe. And unfortunately, not all post-construction cavity fill companies are unscrupulous or competent. So you will sometimes find that a timber frame property has got a filled cavity. And unfortunately, that fill really needs to come out because it is going to present a problem in the long term with damp infiltrating into the timber frame, causing decay.
How would that be seen on a survey?
If it's blown, there might be telltale holes that show that it's it's been blown into the cavity. The seller may advertise the fact that it's got full cavity insulation. Otherwise, it would need an intrusive, hole through the outside.
So if you see cavity wall fill holes on the outside,
Yeah.
it might be a proper cavity wall with cavity insulation, or it might be a timber frame which has been done inadvertently, and because it's got fill holes on the outside, you think, oh, it can't be timber frame, it's got fill holes.
Yeah, I that's like using the argument, it should have been done properly. Doesn't mean it's all right. Yeah, I think you have to first of all decide if it's a timber frame property and decide whether there's a full cavity insulation risk. Insufficient wall ties, I don't know that that's a common problem. The technology of wall ties is slightly different because they're not built in as the masonry as a masonry cavity wall proceeds. You build them into the wall. With timber frame, they have to be fixed to the timber frame. Not something that you have to be on the lookout for normal wall tie failure type evidence. Long horizontal cracks in the masonry. Poor provision for shrinkage. I come across a property where it had 3 stories of masonry and then the top was lead clad, and that was all buckled around the bottom. And when we looked at it upstairs, it looked like there was insufficient clearance. The cladding was dressed right over the brickwork. So buckling in the masonry or in any cladding where the two abut could be signs that there's been poor provision for shrinkage. Now, as we come to our close now, altering timber frame properties. Probably something that's quite tricky. And in looking at surveying properties that may be timber frame, look out for alterations that have been done. And if there are alterations which would have involved removing walls, I think it's doubly important that a building regulation certificate is available and perhaps even evidence of a structural engineer's input. So I've considered 3 scenarios: removal of an internal wall, removal of an external wall, and a loft conversion. With the internal wall removal, you've got several things here which would apply to any wall removal in any property. One of the main differences is that you're going to get concentrated loads on the foundations at either side of the opening because you won't get any load spread. You may also lose racking resistance. Now, that does apply to masonry walls as well. You need a certain amount of masonry cross walls in a building to make it stable. The same applies to timber frame. If you're removing an external wall, you've got exactly the same issues, but any brickwork that is going to have the ground story removed, you need to really support that on steel and not timber. And I illustrate that here. If you have an extension out, the brick wall above needs to be supported on a steel beam, and that steel beam is likely to be on steel posts. It could go onto the masonry if it's not too big an opening and you can avoid the ends of the steel beam being visible, but otherwise it's steel posts. Loft conversions. Inevitably, with any loft conversion, you're going to have high concentrated loads from beams within the loft conversion. Those loads may be able to be carried on the studs that are in there, provided you can spread the load over several studs and they have capacity. Otherwise, there is a possibility that you need to put additional studs under those loads all the way down to the ground floor. So here's a loft conversion I prepared earlier. You'll see that this ridge beam is supported on a spreader which is specified as having to be over a minimum of 4 studs. These studs were calculated to have a little bit of spare capacity in them and could carry that extra bit of load. But with the floor beams, there wasn't that possibility. Now, something I'd found on a previous job where a client had sought a second opinion from another engineer, they had said, rather than put studs all the way down to the sole plate, why not take the beams through the timber frame and support it on the masonry? So that's not something I've thought of. It seems there's a couple of things about it that perhaps a little bit worrying, but it seemed to go all right, so I pinched the idea on my next job. So we had front to back steel beams, so I had a saddle which sat on the outer skin. I specified a gap over the top of the sole plate, and then the main steel beam had a moment connection onto that little saddle. So that may be your only alternative, because to put extra studs in all the way down to the sole plate is extremely disruptive.
So are you burying that onto the outer leaf then?
Yeah, buried onto the outer leaf. Sorry, yes.
Did it work?
I keep looking at my post every day and I don't have any hostile correspondence as yet. That is a distinct possibility. I leave that to the architect to decide whether or not that's an issue. Okay. Well, thank you very much for listening, and I hope that was informative.